Once more, it's that season. Meteorologists expect La Niña to set in only a few weeks, and possibly bring us a harshly cold and turbulent winter. But what exactly is El Niño's chilly sister about? How does this regular anomaly develop? And what impacts should we prepare for in the future? Well, one thing is already clear. Despite the fact that El Niño and La Niña are generally viewed as the major players in global climate, we shouldn't disregard that the polar vortex also has a significant impact on what is happening on our doorstep. Indeed, the exceptional interaction between the polar vortex and La Niña may this time guarantee that we are in for a winter entirely different from those of the past. Droughts, severe flooding, and abrupt temperature fluctuations are unfortunately becoming more frequent with an unpleasant level of certainty. According to experts, they are also becoming increasingly likely. Scientists don't need to look far for the justification behind this unwanted development. Climate change has already increased average annual temperatures globally by 1 degree between 1881 and 2019. In this country, the increase over the same period is as much as 1.6 degrees. The 10 hottest years since regular weather records began have been measured starting around 2010. However, even the outlook for the future cannot be described as especially optimistic, considering expert forecasts. Regardless of whether we succeed in immediately stopping the warming of the Earth, certain climate-related changes can no longer be prevented. In Germany, the increase in extreme weather events is particularly linked to the risk of storms, extreme heat, heavy precipitation, and consequently flooding. We only need to recall the 100-year flood of 2021, which claimed a total of 180 lives, 135 of them in the Ahr Valley alone, and caused billions of dollars in damage. At the same time, however, the disturbed climate during the winter also causes abrupt temperature drops that are as surprising as they are sudden. Despite the fact that we have largely looked in vain for a winter wonderland covered in snow and ice in recent years, the United States faced an exceptionally cold spell in December 2022, which claimed at least 63 lives. In February 2021, the situation in Texas was even more dramatic. The lowest temperatures in 30 years claimed 250 lives. Despite steadily rising average temperatures, meteorologists point out that such events are not isolated cases. Quite the opposite. According to the National Center for Environmental Information, the frequency of extreme blizzards has increased in 2/3 of the eastern United States. Clearly, the data in question pertains specifically to the United States. However, researchers emphasize that similar developments can be seen in other parts of the world. But why is that? What are the reasons for this apparent climatic inconsistency? How can a planet that is actually getting increasingly warm experience dramatic cold spells and sudden ice storms at the same time? How do El Niño, La Niña, and the polar vortex influence the weather? Well, the answer to this question is complex, to say the least. Recently, atmospheric physicists announced that they had identified the true culprits behind these often contradictory weather phenomena. According to them, the interaction between the polar vortex, El Niño, and La Niña seems to be responsible for the extreme events of the past. Before we go into more detail about the developments that could result for us in the future, we should first clarify what is actually meant by this trio. Experts use the term polar vortex to describe the low-pressure vortices that exist at high altitudes over the North and South poles. These vortices regularly intensify during their respective winters, which is not surprising since the lack of sunlight means that the atmosphere cannot warm up during this time. As a result, cold air accumulates, and the westerly wind systems associated with the polar vortices intensify. Regularly, the winter polar vortices are very stable over the poles. However, if the polar vortex weakens, for example, due to strong warming of the stratosphere or splitting of the vortex, the current in the vortex weakens and ultimately becomes unstable. As a result, pockets or lumps can eventually develop, which can lead to a polar outbreak, or in other words, a movement of extremely cold air masses. Archaea are single-celled organisms known for their ability to thrive in extreme conditions, such as underground hot springs, salty lakes, and deep-sea hydrothermal vents. Some can survive at temperatures above the boiling point of water, while others live in extremely acidic or basic conditions. Their ability to adapt to extreme conditions suggests that they may have been among the first life forms to colonize early Earth. These prokaryotes dominated the early Earth, but a major leap in complexity came with the development of eukaryotes around 1.5 billion years ago. Eukaryotic cells are more complex than prokaryotic cells, with a nucleus that houses genetic material and specialized organelles that perform different functions. The origin of eukaryotes is linked to a process called endosymbiosis, where a larger prokaryotic cell engulfs smaller prokaryotic cells, which then become beneficial partners. Over time, these engulfed cells evolved into organelles like mitochondria and chloroplasts. Mitochondria, often called the powerhouses of the cell, produce energy through cellular respiration. Chloroplasts, found in plants and algae, enable photosynthesis. This endosymbiotic theory is supported by the fact that mitochondria and chloroplasts have their own DNA, which is similar to the DNA of certain bacteria. Around 1.6 billion years ago, the first multicellular organisms began to appear. One of the earliest known examples is Gonialax, a type of green algae that lived in shallow oceans. Gonialax was a simple ribbon-like organism, but its appearance marked a significant stage in the evolution of life. Multicellularity allowed organisms to grow larger and develop specialized cells for different functions. This increased complexity paved the way for the diverse range of life forms that would follow. Comes from old stone developments all over the planet. These fossils show a wide assortment of shapes and sizes, demonstrating that acars were a different bunch around 1.2 billion years ago. Red-green algae, or Rhodopa, arose as part of the earliest photosynthetic organisms. Red-green algae are still around today and are normally found in marine conditions. Red-green algae have an exceptional pigment called phycoerythrin, which gives them their red tone and allows them to absorb light effectively for photosynthesis. This adaptation enabled red-green algae to flourish in deeper waters where light is limited. Fast forward to around 600 million years ago, and we enter the Ediacaran period. This period is characterized by the presence of a group of early multicellular life forms that lived in marine conditions. The Ediacaran biota included an assortment of odd and intriguing life forms, some of which have no modern-day counterparts. One key example is a flat, round animal with segments named Dickinsonia, which lived around 550 million years ago on the ancient seabeds. It was well adapted to life on the ocean floor, where it fed by absorbing nutrients from microbial mats. It grew up to 4.5 feet long and is the oldest known animal on Earth. It existed long before the Cambrian explosion, when most major animals began to appear. The new Earth was a hostile place during this time. The movement of the mantle beneath the crust caused the development of large tectonic plates on the planet's surface. Collisions of these plates created massive mountains and volcanoes that continuously erupted, spewing out huge amounts of magma and gases, and reefs were formed in the seas. At this time, the protoplanet barely had an atmosphere. However, as the planet cooled, gravity trapped those gases from the volcanoes, and water was stored on Earth through the impact of many comets and asteroids. Another key factor for life to emerge on our planet, besides water, is its position relative to its star. The Sun Earth sits in what's known as the Goldilocks zone, which places it close enough to the Sun to allow liquid water to exist on the planet's surface. Before life even began or had a chance to take hold, radiation from our star was the primary source of energy on the planet, just as it is today. The early Earth had almost no oxygen, if any at all, and it is hypothesized that solar energy provided the kickstart that transformed simple organic molecules into more complex ones, turning them into the building blocks of chemistry and life. Life probably developed in undersea alkaline vents, and was likely based on ribonucleic acid, RNA, a nucleic acid found in all living cells, as opposed to deoxyribonucleic acid, DNA, an organic substance containing genetic data and instructions for protein synthesis. Eventually, during this time, a common ancestor led to two main groups of life, bacteria and archaea. Although exactly how this happened is still uncertain, for billions of years, tiny microorganisms and single-celled organisms evolved and began benefiting from methane around 3.6 billion years ago. By the long-term mark, evidence of viruses was found. However, some contend that viruses could be as old as life itself. At some point during Earth's early history, the planet took a turn toward livability when a group of organisms, known as cyanobacteria, evolved with the ability to convert light and water into energy and produced oxygen in the process. Dissolved oxygen created iron particles in the seas, rusting and sinking to the ocean floor, which formed striking red iron oxide formations. But between 2.4 and 2.1 billion years ago, something extraordinarily wonderful and terrible occurred in this early phase of life. The toxic waste created by these evolved photosynthetic cyanobacteria caused oxygen to build up in the atmosphere, leading anaerobic bacteria to die off, triggering the planet's first mass extinction event, which some call the Great Oxygenation Event. How could oxygen be harmful, you may ask? Oxygen became toxic because of its high levels, which overwhelmed the natural antioxidant defense system of any living microorganism or bacteria at the time. Essentially, these cyanobacteria, like algae, ate themselves to death and caused a global extinction. But the worst was yet to come. Around 2.3 billion years ago, the Earth froze over, possibly as a result of the Great Oxygenation Event and volcanic activity. Over time, the ice melted, which led to more oxygen being indirectly released into the atmosphere. This gave way to the Neoproterozoic era, where protozoans such as paramecium, amoebas, and melanocytic organisms evolved. The first animal cells were different from plants, and these cells began feeding, benefiting from plants, and became the first herbivores. Yet during this period, Earth froze again at least 2 more times, which slowed evolutionary development. However, life found a way, and during this time, parasites, worms, and other small, mutually balanced creatures survived. Fast forward to the Paleozoic era. Complex life forms began to develop, including fish, arthropods, mollusks, and echinoderms. Plants began to appear on the Earth's surface, and air-breathing creatures started to walk, creep, and crawl on land. In the meantime, sharks, horseshoe crabs, and starfish began to fill the seas.